Two more than for yeah.
Please let me know if you can see the whiteboard. Please, can somebody, Madam Prudence, can you see the whiteboard? I need somebody to be talking to you. All are just quiet.
Yes, I can see
And I
it.
don't know if you're all seeing me.
I'm seeing the whiteboard, sir.
Okay, good. Awesome. Okay, great. Okay, today we let me start by apologizing for coming late. I traveled and it just got me hooked up somewhere. So today we're gonna do something. We're gonna go into a concept. We're not actually taking one new model today, but we want to touch a concept that is very important because going forward we're gonna have this coming up regularly and we have to discuss about it. So I thought it wise to look into that this class, and then before we go ahead. And the reason why, again, I think last class best man made mention of these particular concepts, and so I just thought it wise that this class we should clear it out before we go up, so that as we talk about it regularly, people should be able to follow along. So just a recap of some of the things we've talked about. We started looking at the linear regression model, and we say the linear regression model does functions by, drawing a line of best fit. And I said, if I have my points like these, right, this can be my point, and my data is supposed to be sort of linear. And if you look at this is a positive correlation, right? It's a positive correlation. So if I can have my line of best fit like this is my line of best fit. This is what we talked about. And we discussed how the machine gets this line of best fit, right? We talked about all of that. Now, this, if you notice, the machine draws a line of best fit, meaning that it does not necessarily, there's another thing that the machine would have also done, right? It would have also done this. Let me give you all the three different scenarios, right? But then I would have to reduce my graph and make it smaller so that I can be able to fit in all the three scenarios. It would have also done, let me draw a smaller graph, okay? So that I can fit in all the other possibilities. It would have also, let's say these are our points. And then let's draw another line graph down. Let me make it bigger a bit. Please pay close attention. I'm trying to build a case here, so that when I finish my case, you people cannot petition. So this one I can just, let me just plot some points again. These are just some points that are plotted. Now, this is case, let's call this 1, 2, and 3. And then this is what I'm going to do. I'm going to do the, right? No. I think this one is a bad line. Let me draw a different one. Maybe I draw it like this. Maybe. Okay. This is the first line. This is case 2 now. In case 3 is like this. Maybe it did not reach this other guy over here. Let me draw case 3. So my case 3 line is like this. Let's start with let's have a small Q&A. Which of these cases will give us the minimum error? Which case will give us the minimum error?
It's 2.
Good. That man says case 2. Who has another option?
Is 1.
Okay. Mr. Tony says case 1. Who thinks otherwise?
I wasn't the one that said it to.
Okay, sorry. Who said case 1? I wasn't looking.
I did.
Is that Tony?
It's
No.
Benito.
Oh, Benito. Okay.
Yes.
Okay, Benito. Benito says case 1. Okay. Are those all the proposals? Why are you not thinking that case 3 can have the minimum error? Let me just ask. Those that did not say anything. Okay, awesome. Now let's discuss. You remember the error again, like I always say, will be the difference between the actual data point and the predicted data point. And so if you notice, we use the line of best fit as our predicted to get our predicted data point. And if you notice in case 2, you notice that if this is my actual data point, and then if I want to get my predicted value, for example, let's say this is 1, 2, say 3 here, 4 here, 5 here, and then maybe 6 here, right? If I get for the point 1, 2, 3, 4, 5, 6, if I say what is the actual value of 1, this is where 1 is plotted. So it has a corresponding value on the y-axis. So I'll go up. I notice that this is where 1 is, and this is where it meets. It gets a corresponding value here, say 10. And 2 will fall exactly on the same position, and it gets a corresponding value, say 15, for example. You notice that the difference, there will be no difference between the actual and the predicted, meaning that the error will be 0. Because if I bring a new point now, for example, if somebody comes and say, my GPA, because we used to call this GPA in our last class, right? My GPA is 2, and then they ask the algorithm, can you predict the salary, which is going to be our y-axis? Say my GPA is 2, can you predict the salary? What the algorithm will do is we'll come and look at 2, and you notice that if it maps 2, it will fall exactly where the original value of 2 was during the training. It will give it the exact value. The same will apply to 4 and all the other values, because why? They are all on the line. But for case 1, if you come to case 1, look at, for example, let's look at a point like this point. If you look at a point like this point, let's assume that this point applies to maybe, let's say, 5 here. And if you notice, this is the exact, if you take this point across this way, it will give you a value, let's say 10 here. But if you follow this same point and use the line of best fit, you see that the line of best fit gives you a value pertaining to maybe 15, for example. So you notice that the error here will be 10 minus 15, which will be, when you take the absolute, it's going to be 5. So most of the time we always use the absolute. That's why you remember when we were doing that performance matrix, we either use the absolute or we take the difference and then we square it. But so if you take -5 squared, it is going to give you 5. That's at 25, positive 25. And again, we said this was not a good matrix because positive 25 is not a representative of an error. That's why we used the next one, which was the mean square, which was the square mean error. You remember that one where we actually now have to take the square of 25, which will now come back to 5. So it's just something we discussed in the last class. I just want to remind you. And so you notice that the error here will now be in magnitude will be 5. In magnitude will be 5. So the error here was 0. The error here is 5. Now, if you do the same here, you'll notice that the error is even worse because all the lines, all the points are completely away from the line. So the error is worse. Every point, the sum of error will just be very high. Now, under normal circumstances, right, you would have said, because remember the idea behind the linear regression model, for example, that we talked about was that it's going to calculate, it's going to put the line of best fit such that the error, the sum of error will be minimum. Therefore means we would have been saying that this case number 2 should have been the best case because why? The sum of error is minimum. Because the sum of error is minimum. But then we are going to have some 2 concepts today that are going to come into play, and we'll see why this case number 2 is not the best ideal case.
Okay. So, question,
So,
please.
yes.
I was just going to, I thought maybe we're landing on the fact that the answer is 2 as the scenario 2. But I don't know. The final answer is scenario 1, right?
The question was, which of these has the smallest error? And the right answer was case number 2. It has the smallest error. But the question is,
Oh,
which of them will be best for prediction? It will not be case number 2. That's what I want to
ah,
address now.
okay.
Is it
All
clear?
right. Yes, that's
The
fine.
fact
That's
that it
fine.
has the smallest error, it doesn't mean that it's going to be best for prediction, right? And those are the 2 cases I want to address now. Is that clear? Because like I said, our ideal situation would be that the line of best fit should give, our line of best fit should give us the least sum of error. And to think that the least sum of error is going to be 0, that would be very nice. But then is that going to be? So let's talk about 2 cases here that ideally you will not find yourself having to do that. So this case number 1, we'll call case number 1 normal. And then I'll introduce some 2 terms. Here I'll use the term is called overfitting. And here you call it underfitting. Underfitting. If the spelling is wrong, take the spelling and leave me. Take me and leave the spelling, please. So underfitting, overfitting. Now, here you will have something that we call high. These are another term. I've given you 2 terms, overfitting and underfitting, which we are going to dwell highly on. So here you have something we call high variance. This is the 3rd term. And then here you have something we call high bias, and the 4th term. So we've talked about 4 things. 1, overfitting. And please, for some reason, if this is not clear to you, just look down on your whiteboard. There is a zoom button there. You can increase the zoom. Maybe some of you are actually struggling to see what I'm writing because maybe your zoom is small.
Yes,
Look on your
I
screen.
am.
Look down on your screen. There is a zoom button there. Bottom right, there is a zoom. There's a zoom bar there. Just click on the plus. It's going to zoom it for you. And it's an interactive dashboard. You can be moving it up and down as I'm going. Is it okay, Mr. Tony?
I'm trying to, and it's as if I even write it, to write on the board as well.
No, Mr. Tony, look down bottom right. There is a bar there with a zoom, with 2 zoom buttons. There is a minus zoom and positive zoom. Click on the positive zoom. It's going to increase the size of what I'm writing on your own screen, not on my screen.
Sure, I've seen it. Thank you.
Yes, it's going to increase it. And then as I'm going, and whatever I'm doing, if I'm going down, you should also move your You can use your mouse to move the board up as you're following what I'm doing. It's an interactive dashboard. Sorry, it's an interactive whiteboard. So you can follow along because I'm writing and going down. If you're not following, you'll notice that it has gone down and you are not seeing again. So you have to push it up to be able to follow what I'm doing. Okay. This applies to everyone. Eh? Number 2, we are looking at underfitting. Underfitting. Number 3, we are looking at, let me just use the term variance, and then we're going to break it into high and low variance. And then number 4, we are looking at the term bias. Okay. Bias. Let's start with overfitting. Now, Mr. Tony, let's have a discussion. Are you there?
Yes, yes.
Let's have a discussion. Have you thought of a situation, or you know the time you were still in secondary school, high school, and all those times? Did you ever do
Yes.
the thing that we call cramming?
Yes, after writing the thing, you just forget it.
Okay, good. So you did cram work, Abi?
Yes, so in medical
And
school, yes.
yeah, and so what you used to do is that when the teacher comes to class and give the notes, you go and read the words. And most of the times for the cram work, if you come and you're writing and you miss one word, the whole thing disappears in your head, right?
Yeah.
And at times when you come and you are trying to remember the thing that you cram and it's not aligning, and your one word is not coming into your head, the whole thing that you cramp in your head disappears. Then again, with cramming, what happens is that if the teacher comes now, let's assume that what you read and cram in your head, there's something we used to call speco. I don't know if people know. They used to say when you are thinking that the teacher will come and give some particular question, one particular question in the exam, what we do is that we go and cram the answer of that question. So, and then the way the question has been said, we just say, for example, if they say define machine learning, we go and cram the definition of machine learning the way it is, knowing that the question is going to be define machine learning, such that if the teacher comes and then gives the exam, and on that exam paper we see define machine learning, we just gonna copy and paste the thing that we saw in our books on that paper. But now, if they come and now change that question and say, in your own words, what do you think is machine learning? It's the same question, right? But they've changed things just, and then it now needs you to be able to reason, right? So now in this case, let's look at 3 students. 3 cases of students. Student 1. So during studying, student 1 spent time and then read the definition of machine learning and then understood the definition of machine learning. So student 1 understood. So let me use the word understand. And then student 2, let's talk about student 2. Student 2 did what we call, I don't know how they spell cram, so I'm just going to do it my own way. It's whether it's something like that, it's cramp, I don't know. Let's say student 2 cram, and then let's say student 3. Maybe student 3 did not, maybe the student 3 only understands Igbo. Mr. Tony, the student 3 does not even understand English. The student 3 only understands Igbo or Yoruba. So student 3 maybe did not even understand the language that the teacher is using. So the student 3 did not understand. You understand? Now,
Yeah.
let's look at, I'm building a case. Okay, now during exams, or not during exams, during when the teacher is teaching, when the teacher just teaches and finish, the student who has cram, then the teacher will ask questions after class. Once the teacher just finished teaching and ask, what is the definition of machine learning? Of all these students, which of these students will perform best? Normally the one who has cram, because the student will say it word for word. right? Because the student cramped it. You understand? But then if the teacher now talks about application, maybe say, in your own words, what do you understand by machine learning? The student who understand definitely will be able to answer that question better. But this student down here, because of language barrier, will not even know what they are talking about. So these three cases apply in machine learning as well. A situation whereby you have your model or your algorithm behaving as if it has crammed the data that you gave it during training. A situation whereby the model is behaving as if it understood the data that you gave it during training, and a situation whereby the model behaves as if it did not understand anything that you said during training. Now, what are these situations? The first case is the case where the model behaves as if it crammed the data. If the model crammed the data, then the model will perform well. If the model crammed the data, then the model will perform well. Please take note, during training, and perform poorly during testing. Again, think of the student who crammed in class. When they ask the questions immediately after class, because the student just crammed the thing word for word, the student will say it word for word, and it will even be very nice because it will be like the same way the teacher gave it, and it will be so accurate. But now, if you twist that question around, that needs some level of reasoning to be able to answer the same question, even for that student to reason it and say the same thing that he or she crammed, the student cannot perform well. So that's the same case with an algorithm. There are situations whereby it will behave as if the data that you've given it during training, it has crammed that data. And so when you ask the performance of that matrix immediately after training, during training, when you test it, it will perform very well during training. But then during testing, when you go down and give it a test data and say, now take this test data and do a performance, you get poor results. So, for example, during training, the matrix might be, say, 95%. And then during testing, you'll get something like, say, 70%. This in machine learning is called high variance. And this is caused by what we call overfitting. This is a situation of overfitting, and this is this situation over here. This one. Because it's like the machine cram. That's why you see it following the thing line by line, just trying to map through all the points, right? It's a situation of overfitting. And a situation of overfitting will mostly lead to what we call high variance. It will perform well during training, but during testing, the algorithm will not perform well. Is there any question? Those that did not understand anything that I said, put your hands up.
So when you, can I go ahead?
Yes, please.
Yeah, so I'm trying to wrap my head around the whole thing. So when you say testing during training, is it like, you are giving this this thing, you have given it data to train on, right? Then after it's done,
Yes.
but during that process, you also give it some data, like that thing you are doing on Tuesday,
Yes.
where you give it I think 80% to train with, or then 20% for
Yes.
testing, something like that.
Yes.
So it's in that period that you are doing it. Then when you now say doing testing, let's say you are done, then you are now bringing
Want
like
to use it?
data, different
Yes.
data, to give it. for the
Yes,
testing,
yes.
like differently. Letter. Okay.
Yeah. And that is why when we go further, you will see the kind of things that cause what we call overfitting, and you understand exactly what I was talking about. You see the things that lead to, the things that contribute to overfitting. You understand? Like Bestman was trying to say the other day, there are situations where we will talk about them as we go down. Situations whereby the model has seen the data before. It's like SPECO, the question, the exam leaked. So the model saw the data and then kept it in his head. So when you came back and asked it, what is this? It just gave you the answer, word for word, right? And so now, but when you bring completely fresh data that is not related to what the model saw, the model performs completely bad. We're going to see, like, we'll see the situations that lead to overfitting. We're going to go down as we proceed. You see overfitting that comes as a result of pre-processing, and overfitting that comes as a result of there's this other one, I've forgotten the name. But as we go down, I'm going to show you all the possible scenarios that can lead to overfitting. But is it clear as of now? Is it clear for everyone?
Excuse me, sir.
Yes, but Benito.
Yes, just to be more clearer. I thought maybe when you train the model better, that's with more data, it should perform, the testing now should be almost accurate, you should have more perform better. That's because of the enough training you've done for it. But I don't know, I think this one is like the reverse of what I had in my head.
Oh, no, it's not a reverse. What you said is perfectly correct. That is why, again, when we'll be looking at bias, which is a situation of underfitting, you'll notice that one of the reasons why an algorithm will not perform well during training and during testing, because the situation of bias. For that reason, let me just talk about bias. Bias is a situation whereby your algorithm will perform poorly during training and during testing. And one of the reasons is because of not giving that algorithm enough data. It's just this, when I'm talking about these things, that's why machine learning is a situation whereby you make machines to behave like human beings. Put yourself in the position of a computer. If I come here and I want to teach you and I don't give you enough information, will you understand what I said?
Exactly.
It's the same thing. So if you come and you give that machine small data during training, and then you come and use, and then you come to test that algorithm did not understand. So it will perform poorly. So that's one of the reasons you see for underfitting, which is a situation like this, a situation like this one. Yeah. This is a situation of underfitting. That's one of the reasons why an algorithm will underfit or will not draw a good line of best fit called underfitting is because of bias. And one of the causes of bias is not having enough data to train the model. The second reason is having data that is not well cleaned, or speaking a language to the computer that the computer does not understand. That is the kind of student. You remember student 3, that teacher was teaching in English and student 3 only understands Igbo. I told you the other day that computers only understand numbers. So if you come and train your algorithm with data that has letters, you are on your own. When you come and ask that algorithm anything, that algorithm will still be looking at you the same way. It did not understand. It's like speaking English to an Igbo guy who doesn't understand English. Does it make sense?
Awesome.
Bro, this one you're calling Igbo language, Igbo. What happened? Did you date somebody that is an
Because
Igbo
I
person?
started talking to you and I know you're in Nigeria, right, Mr. Tony? But does it make sense?
Yeah, it does. It does.
Okay. Again, we'll look at the causes of overfitting. But again, let me just recap. Variance is a situation whereby your algorithm performs very well during training. That's why the word vary comes in. Vary is it's an English word, right? So high variance means the algorithm performs very well during training and then perform poorly during testing. And like Mr. Tony Riley said, when you train the algorithm and test it immediately, it did well. But now we started giving it fresh data, which is actually the real job that algorithm is meant to do. it start performing poorly. For example, let's look at that our algorithm that we were using to test to predict salary using somebody's GPA. We took that data, there were 200 records. We splitted those 200 records and we trained that algorithm with 160. In those 100, in that 200, we take out 40 to keep for training, for testing. We train with 60, 40, and then we 160, and then we test with 40. Now, it would have done well, it performed well. Now, the next thing is that now, because this was when we were developing the model, now we deploy this model into our environment, and then we are now using this environment now to be able to hire workers. So when people just come, when the moment somebody just come to the office and is looking for a job, we just ask, what was your GPA? The moment the person gives the GPA, you just pass that GPA to the model. You expect that model to give you a good salary based on the training. But now, subsequently, instead of now giving you a good salary, the model starts giving you something that is so unrealistic, right? That is the kind of situation of high variance. You did well when we were training you, but now that we want you to work, now we want you to use that training and do work, you are now performing poorly. And then a situation of bias will be the situation whereby during training, the algorithm perform poorly, and during testing, it's still performing poorly. That's a situation of what? Bias.
So, bro,
Yes.
let me ask this question. I've been pondering over it. Is there a constant to know the amount of data, and you can say, okay, this data is enough that you can use to train a machine? I don't know if you understand. Like, is there like maybe gigabyte or terabyte or whatever that you can say, okay, I've given this machine, I've trained it enough data, now it can perform the work I want it to. I don't know if you understand my question.
I understood your question, Mr. Tony, but I cannot give you a direct answer to that question. I cannot, because I have not read somewhere where there has been that established value. But what I can tell you for sure is that machine learning is a continuous process. You understand? Like, if you start training your algorithm today and it's not performing well because it doesn't have enough data, you have to keep adding the data up to where you start getting the performance that you want. But there's no cut top value for that. Unless when you come across it, if you read it somewhere, please do well to tell me, because I've also faced that challenge. I don't know if you get it.
Good. Yes, I
And
do.
that's why
Thank
at times it's difficult to solve a situation of bias. You get it? At times it's difficult to solve a situation of bias. Why do I say so? If the data you have to train the algorithm with is the only data that you have, what do? There's nothing you can do. So that's why at times it's difficult to solve a situation of bias. Because like we said, one of the causes of bias is when you train the algorithm with very, very small amount of data. So it did not understand. Right? Anyways, let's keep going.
Please, how can you, in the case of overfitting, how can we solve the situation?
Let's first of all look at the causes, and then we'll see how to solve it.
Okay.
We'll see how it can be solved.
Okay, sir.
For us to look at the causes of overfitting. Now, let me explain something. Oh, I don't know if please give me a minute. There is some good example I used in one of my lectures somewhere. I think a lecturer was teaching a group of medical personnel from Ghana. I used a very good, there was one very nice example I used. And let me try to source it from let me see if I can see it from my collection, my notes. Oh, let me see, it's supposed to be GM. If I come here. Okay. Let's talk about something. Please, you have to follow me carefully, okay? Follow me carefully as we treat these concepts, because these concepts are very important. I know we talked about these during the start of our class. We looked at different data types. We talked about nominal, categorical, numeric, discrete. We talked about all of these things. Nominal, discrete, continuous variables. We talked about these things from the very, very, very start of the program that we're looking at. And again, that was very important, because now I'm going to say something. Now, when you have data, let's say my data is yes, no, right? Now, what I'm saying yes, no is my target. Let's take an example. Cancer. They say you have cancer, yes. Cancer, no. This is my target. So you use your features to predict whether somebody has cancer, yes or no. Now, normally we know that you don't send this to the algorithm. So most of the times you have yes represented as 1 and no as 0, right? This is called encoding. Encoding. And there is a particular kind of encoding which is called one-hot encoding. Now, one-hot encoding is used to solve situations like this, where your variable or your options, let me say your categories, are just, or your values are just yes and no, right? Where your categories are just yes and no, they are just two binary, for example. Now, it is also used to solve a situation whereby your variables are going to be having many your categories. For example, let's assume that you have some data and you are using that data to predict somebody's disease status. So under disease, we have positive, negative, invalid, and then undetermined. How did I spell this thing? Undetermined. So let's say these are the 4 categories in your data. And you use this you want to encode this data. So let's draw a table here. So let's say the disease outcome is going to be, let's say outcome here. And then let's just call this your feature. It can be anything, whatever you're using to predict the disease. Now, in a situation like this, what the algorithm will do is that it will create columns. 1, 2, how many are there? 1, 2, 3, 4. So it will add 3 columns. Here you have positive. Here you have negative. Here you have invalid. And then it will not create a column for this one. Let me explain. So now let's look at the record 1. Let's say record 1 or number 1. The outcome, let's say positive, negative, positive, invalid, positive, undetermined. Undetermined. Oh no, let me change this undetermined here to say maybe negative, for example. So now what it's going to do is that It's going to create multiple columns. When it comes to positive, what it's going to do is that it's going to put here for this record. So we are going to have this thing running like this. Let me show you. So record number 2, record number 3, record number 4, record number 5, record number 6. So what it's going to do is that for this column here is going to put 1 and then put 0, 0. Because this column was positive, so on this record was positive. So under positive is going to put 1 and then put 0, 0. Under negative is going to put 0, 1, 0. And then on automatically undetermined here is 0. The algorithm knows that, so it doesn't always add up to the number of columns, but know that it will not add the column for undetermined. So let me just put it here just for the sake of explanation, but it doesn't do that. It automatically just know that if this one, for example, if this was, let's come down to this one, assuming that this column is not there, and then let's come to a situation of undetermined. You will normally be 0, 0, 0. So if it's 0, 0, 0, then automatically undetermined is going to be the option. So that's why it doesn't always add that column. So, but for this case, you have 0 here, 0 here. Positive here, you have 1. And then here you're going to have, what is that? 0, 0, 0. Invalid, you are 0, 0, 1, 0. And here you're going to have, what's this? What's the error here? Is it positive? Positive 1, 0, 0, 0. And then here will be 0, 1, 0, 0. This is called one-hot encoding. So this is how it encodes the data. And now, when the algorithm encodes the data like this, it causes a condition called data leakage. It causes a situation called data leakage. And data leakage is like what you call like when exams leak, or you understand when something leak. You know the word leak now. You know when you are doing something and then they want to give you an exam, but they can't, for some reason, they mistakenly show you the exam paper and you see the questions. That's called leakage. So during training, when you train an algorithm with data that has been encoded like this, when you train an algorithm with the data that has been encoded like this, what happens is that you have leaked that data. Because how do you leak that data? Look at it. Look at it. When you take 0, 1, like as I was explaining, when you take 1, 0, 0, 0, let's assume that during training we cut these ones like this and then train, and then during testing now we have this thing like this. We take this one down. You notice that for a particular record it has turned positive and is 1, 0, 0, and then therefore means it just keeps that value in its head like that. So when you come again and you use that same value to train it to, am I really putting this the best way that I can put it? I feel like it's not aligning in my head. Again, how does data leakage? Please just hold on again. I've missed something about this data leakage during how does data leakage one on encoding. Okay, yeah, I think I was on the right track. I just wanted to be sure that I was explaining it correctly. So now you notice the pattern that we are following to encode this data. Positive 1, 0, 0, 0, 0. Negative 0, 1, 0, 0. So when you do this during training, the algorithm understands these patterns, and then when you bring that, the algorithm will just master these patterns. And then when you bring that data during testing, the algorithm will just replicate that pattern again and do predictions, and it will do well. But now when you bring your new values some other time that are completely different from these, so you now bring different features next time to predict it with it, you notice that the algorithm does not perform well again, because why? It was able to how do I put this thing in a more simple way? Give me
I
a
was able
minute.
to cram the formal data.
Yeah, it's you're able to cram the formal data, and I'm trying to look at it this way, right? Mm, ah, okay, these are the features, right? These are your features. So let's say we are trying to do disease outcome, and then we are just looking at something here, maybe your weight or something. And so you have that those values for your feature running at this on this column. So what it does is that if you take this column, it takes this feature, it looks at the pattern. It takes this feature, looks at the pattern. It takes this feature, looks at the pattern. It takes this feature, look at the pattern during training. And so what happens is that if you now come and once you cut the same data set, that and so what, because when you are doing encoding, you know that you do that encoding in one data set at the same time, right? It's one data set, so you encode the data set at the same time. So what you do is that you encode the data set, then cut half of the data set and keep it out for training, right? And so when you keep out that data set for training and testing, you use the same data set, that the same patterns that you had shown that algorithm during training to test that algorithm with it again, and definitely you expect the algorithm to perform well because it already do what we call like the cramming work that we are talking about. Now, when you bring a completely new data set, mind you, the patterns might not be the same for the encoding. And so since instead of understanding the algorithm rather mastered by the pattern, remember these algorithms are smarter, I don't know, as days go by, they become smarter than human beings. So you are looking at this thing, you as a human, you might not pick these patterns, but machines will do. Let me tell you. That's why when you are looking at deep learning, there are times that you look at output from deep learning and you're wondering how that output came about. But machines are good at picking patterns in data. And so it's going to pick this pattern and it's going to use it to predict the values in the test data that you are going to supply. And during training, that algorithm will perform very well. Now, when you now bring completely new different values with the way the encoding flow is different, it's going to perform poorly because the pattern now is different. So instead of understanding the data, the algorithm was busy understanding the patterns. Does it make sense? And so to avoid this problem, what they always do is that when you want to train your algorithm and test it, what you do is that you separate the data before you encode it. Like you separate your data into train and test before you encode it. You encode the training separately and you encode the testing separately. Is it clear?
Yeah.
So, sir, just in a nutshell, you're saying that if we encode before training and testing, we could have difficulties. We could encounter a situation of bias, maybe. But
So what I'm saying is that if you encode all your data set before splitting it into train and test, you have what we call data leakage.
okay,
And data leakage will lead to what we call high variance. Is that clear? So to avoid high variance as a result of encoding, you have to split your data into train and test before you encode. Because normally you will not send this positive negative to a machine learning algorithm. No, this is what the algorithm will get.
That's right.
Not this positive negative. You understand what I'm saying? So before you go ahead and split your data into train and test, before you encode your data, make sure you are split it into train and test, and then you encode them separately. Is that okay?
That's
Now,
understood.
another situation of leakage is this. Let's assume that you have a column. And so you have column, this column, let's say this is your outcome. And then there's another feature here. Let's say this feature. It can be somewhere here. It can be within here, but let's just put it here. for the sake of convenience, let's say feature C. Let's just call it C. Now we have yes. This is the outcome. Yes, yes. Maybe let me put no here. Yes, and then no. And then on this column is a feature, is not the same as the outcome, but unfortunately, for some reason, you also have yes, yes, no, yes, no. Do you notice that these two columns are the same?
Yes. Yes, they are.
And so, if you train that algorithm with this part, and it's using this part as its target, trust me, it's going to use this, it's going to notice this pattern, and it's going to cram it. And now when you bring the data for testing, if it doesn't still follow this same pattern, the algorithm is going to perform poorly. Is that okay? And
That's
that is why
okay.
you
No,
hear
it's not
I
okay,
say,
sir.
look at this. Yes, 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 no, 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 yes, yes, no, no. What I'm saying is that this is part of the what we are going to use to predict. We are going to use this feature one A, B, C to predict D. D is our target. So if I use A, B, C to predict D, you notice that C is part of my features, which the values are the same like the values in D. But C is not the target. You understand what I'm saying? C is not the target. So when you so you notice that because of the fact that C looks the same like D, the machine is going to notice this. And so it's going to cram. So at times when you now come to predict, it's going to now just use the same values for C and just predict the outcome values for D. You understand? So instead of understanding the data, the algorithm rather just crammed this pattern here like this. This is a situation called leakage. It's a leakage. This is data leakage. Because you leaked your outcome here now, right? So the algorithm learns this, and now during testing, it's going to perform well. But then when you bring completely new data that doesn't follow this pattern, the algorithm is going to perform poorly. Are there any questions?
So the bottom line is for us we able to effectively train a model. We take the data and first of all um, split it into as train data and test data before encoding it and then putting it into the model. If I got you correctly.
So there will be a series of things that you do, because the normal situation that we want to get, what we were looking for, is a situation like not this one. This is what we are looking for. We don't want this one. We don't want this one, because we've already talked about the disadvantages of this, right? This one will lead to variance, high variance. This one will lead to high bias, right? So, but what we want is a situation like this where you perform well during training and perform well during testing. We don't want a situation whereby you perform well during training and perform poorly during testing, or a situation whereby you perform poorly during testing and perform poorly during training. No, we want the situation whereby everything is well. So there will be a couple of steps that we are going to be taking to avoid that. As we'll be going ahead, we'll be seeing how these things are implemented, right? As we're going ahead, we'll be seeing how these things are implemented. Now, I started saying that for you to avoid one hot encoding, so this is called, so when you do that during this encoding, that this data leakage that occurs here is called, we call it a pre-processing leakage, because it happens during data processing leakage. That's how we call it. And then this one that occurs here is called target-based leakage. Target-based, because it's like Your target is almost the same like a feature, target-based leakage. So, and I said to avoid pre-processing leakage, I already said this. To avoid pre-processing leakage, we are going to do what we call, what you're going to do is that you're going to split your data into train and test before encoding. And to solve the problem of target-based leakage, there's a concept called cross-validation. There's a concept called cross-validation. There's a concept called cross-validation, which I don't want to go into cross-validation in this lecture today because I've already bombed you guys with a lot. So there's a concept called cross-validation that is going to be used to solve the problem of target-based leakage. Is that clear? I'm talking to Benito. Benito, you asked the question. And I'm trying
Yes,
to make
yes.
you understand that to solve these problems and to be able to train your model accurately, there will be a couple of steps that we'll need to take to ensure that we do not have these things happening. Is that clear?
That's good. That's okay.
And again, for you to be able to do that, you need to be sure, you need to know the kind of data you're dealing with. If you are dealing with multi-category, nominal encoding where you have multiple categories, then you need to know that you have to solve that problem by splitting the data before you encode it. Is that clear?
That's clear, sir. I'm looking forward to an example that maybe you would use. I think it would help us to better understand.
Yeah, well, I mean, we'll do encoding, right? We'll do encoding in future, we'll do cross-validation and all of those things, right? But then it was good that you people understand this concept before we go ahead, because as we start going ahead, as I'll take the next algorithm, which is going to be multilinear regression next week. So next week, what we're going to do is that we'll talk about cross-validation, and then we'll now look at multiple linear regression and its practical example, multiple linear regression, and then maybe linear regression, and then we see how we can do an example. Because last week we just looked at simple linear regression. So the next class we'll look at cross-validation, then multilinear regression, and then how then we do the practicals, and then that should be what we'll do on Thursday. So if for this class you don't have any question, I think we are good to keep it here for today, and then we see ourselves again on Thursday. Any question?
Yeah.
Where's Bestman? I didn't hear his voice. He raised this issue in class last week. Bestman, are you on call?
He's not on the call, sir, but he was
Oh,
earlier on.
he was the one that raised this issue about bias and in our last class. Then I thought
And
I
it's a
should.
very interesting topic.
Yeah, it's a very interesting concept because it's, if you minimize it, you end up doing nonsense, right? You just see how it can affect your outcome in a very bad way, and you'll be there jumping, thinking that you are doing a good job, but you end up producing a model that gives wrong predictions, and that's how they'll just fire you from your work, right? They'll just say you are not competent enough. Okay, see you all on Thursday. Bye bye.
All right, thank you.
I'll upload the notes, okay?
Please, the notes from the
Okay.
last class, the notes from the other
I'll,
class are not on the
I'll upload all of
elements.
that now. Yeah,
All
I'll
right,
upload
Eh,
all
thank you
of that
very much.
now. Plus the notes
Thank
for
you, sir.
encoding and variance. Okay, madam. So I'll upload all of that now. So you have it in 30 minutes time.
Thank you.